Today, I want to talk a little bit about average rate of change and instantaneous rate of change. And you guys know average rate of change just as the slope of a line between 2 points, or the slope of the line. You'll notice the formula here for a slope, the change in y over the change in x. So if you notice my function, f of x, x cubed minus 2x squared plus x plus a half, and it's in green, you can see the curve here. And there's 2 points, point 1 and point 2. So the red dashed line is called the secant line, and you could see as I move this point, that secant line, the slope is going to change. So in blue on this diagram, this is a tangent line because it just touches my curve f of x at one point. And so notice what happens as my point 2 gets closer to point 1. So the distance between the 2 points is getting smaller. Look what happens to the slope of the secant line. So the slope of the secant line as point 2 gets closer to point 1, so that distance between them is approaching 0. You can see that the secant line, the tangent of the secant line, the slope of the secant line approaches the slope of the tangent line. So we're going to use that idea in calculus because we know it takes 2 points to determine the slope. Well, on a tangent line, you would only have 1 point. So how do we find the slope of that tangent line? And so that's where we're going to use the ideas from calculus. And notice what I was saying, as the distance between the 2 points approaches 0, sounds a lot like a limit. Your packet, this first part of that, is demonstrating what I just talked about. So you can see that printed out there in case you need to review that again. So what we're going to look at now is an example. So let f of x equal x squared. Let us try and find the slope of the secant line between x equals 1 and a value of x greater than 1, but very close to 1. And so we're going to go through and complete the chart. You don't necessarily have to set your calculator like that. But again, we have f of x equal to x squared. And we're going to be using the value of f of 1. So I'm actually just going to include that right here. I'm going to put x equals 1. So if you plug in a 1, 1 squared, of course, is 1. If you were to evaluate f of 2, you're going to get 2 squared, which is 4. So then what you're going to be doing on each of these is you're going to be calculating the rise and the run so that you can calculate the slope. So remember, it's the change in y over the change in x. So to find the slope, we're not calling it y, we're calling it f of x. So I'm going to take f of 2 minus f of 1 and divide by 2 minus 1. So that's how I'm going to do this. So to find the rise, f of 2 minus f of 1, I'm going to take 4 minus 1, because remember, we're dealing with the y values. These are the two y values. So 4 minus 1 is 3. And my x value went from a 1 to a 2, so 2 minus 1 is 1. So then that slope would be rise over run, so 3 over 1, or just 3. So then for 1.5, so if I take, now remember, we're always referencing this to the 1 over here, not to the 2. So here we're going to plug in a 1.5. So if you square 1.5, you will get 2.25. So then if you do the rise, you're going to be taking 2.25 minus 1. And if you do that, you get 1.25. And then you're going to take 1.5 minus 1, and you get 0.5. So if you take the rise over run, if you take 1.25 divided by 0.5, you can check this, but you can see that you get 2.5. Now, I'm going to have you pause. Go ahead and do the rest of them. I'm going to fill it in. Of course, I won't know if you copied me or if you really paused it, but so we'll do that. Okay, so taking a look here, if you filled out that chart, we've got these values filled out. So then if we look at 1, we see that the rise, or f of x is 1. So then if you subtract 1 minus 1, of course you get 0. 1 minus 1, of course you get 0. And we can't divide by 0, so we have a problem. So why can't you use this method to find the slope of the tangent line at x equals 1? Well, we can't divide by 0. So secant lines use how many points? Well, when you find the slope of a secant line, it takes 2 points to find the slope of the line. Tangent lines only use 1 point because they only touch the curve in 1 point. So using the fact that the closer x gets to 1, the slope of the secant line approaches the slope of the tangent line, what is your best guess for the slope of the tangent line to f of x at x equals 1? So take a look at what's happening to the slope as we get closer and closer to that point, as we slide the points close together. So go ahead, take a guess, write it down in the blank, because I'm pretty sure you know. Hopefully you put a 2. So now let's use an analogy. So suppose you leave home at 10 a.m. on a trip and you arrive at 12 noon, 2 hours. The trip is a total of 100 miles. How fast are you going at 11 a.m.? Kind of sounds like a trick question, because it is. You don't know. We can't find the actual velocity at 11 a.m., which is the instantaneous velocity, but we can find the average velocity between 10 a.m. and any other time using the fact that average velocity, and you should know this from physics, total distance divided by total time. So the average velocity between 10 a.m. and 12 noon, so if we find the average velocity, we're going to take the total distance, which was 100 miles, and we're going to divide by the total time, which was 2 hours, and so we get 50 miles per hour. Okay, so that makes sense. So then here, we're going to kind of fill out a chart and use this to come up with our average velocity for each of these situations, and then we're going to try and make a prediction of our instantaneous velocity. So doing the same thing that we did before. If at 11:30, remember that we started at, hold on just a second. All right, so we're taking, we're looking at specifically not from 10 a.m., but from 11 a.m., because we're going to eventually try and predict our instantaneous velocity at 11 a.m. So at 11:30, we've gone a distance of 24 miles. Well, from 11, that's a half an hour, so 0.5 hours. So if we want to find our average velocity, we take our total distance, divide by our time, total time. When you divide by a half, it's the same as multiplying by the reciprocal, so we end up with 48 miles per hour. And we don't know the instantaneous velocity because we don't know if that's a good estimate or not. So now let's talk about at 11:15, let's suppose that we had traveled 13 miles. So our time duration from 11 to 11:15, that time duration is a quarter of an hour. You can put a quarter or 0.25, either one. So I'm going to take my 13 miles and I'm going to divide by a fourth. Now remember, dividing by a fourth, I am going to leave it like this on purpose because then I don't need a calculator because I can switch it to multiplying by the reciprocal and we get 52 miles per hour. Is that a good estimate for 11 o'clock? I don't know. So then let's take a look at 11:10. So suppose, now we're being given this. You can't calculate it. We don't have a formula. So we've gone 10 miles. We're being told, well, 10 minutes, how much of an hour is that? Well, that's 1/6 of an hour. So if I take my 10 miles and divide by 1/6, flip the fraction and multiply, you get 60 miles per hour. Is that a good estimate? Don't know. So we keep going. So at 5.5 miles we've traveled at 11:05. So my time duration, 5 minutes out of the hour, so that is 1/12. And we're going to take 5.5 divided by a 12th. And I'll just tell you, this one I wouldn't necessarily get in my head. So 66 miles per hour. Don't know if that's a good estimate or not. Still don't know the instantaneous. So on this next one, 1 minute is 1/60th of an hour. If you take 0.8 and divide by 160, you get 48 miles per hour. You can check if you don't believe me. Still don't know, even though we're really getting a lot closer to 11 o'clock. So, we're going to get a little closer. So at 11 o'clock and 30 seconds, 0.5 miles, that happens to be 1 out of 120. So if you divide that, you get 60 miles per hour. Still not really sure about this. So now we're going to go 1 second after 11 o'clock, and we have 80 feet. Well, that's a problem because we need to have it in miles. So you would need to recall that there are 5,280 feet in 1 mile. So I'm going to have to divide this by 5,280. And when you do, I'm going to write this out a few decimal places. You can see this 1/5 is going to repeat. So that turns out to be 1 out of 3,600. And when you divide that out, you get 54.5 miles per hour. So I just kind of did the math. We still don't know for sure. But at 11 o'clock, the time between 11 o'clock and 11 o'clock obviously is 0. So you haven't gone any distance. You also haven't gone any time. So I can't divide 0 by 0 because it's undefined. So then I have to decide, well, what if I wanted a good guess for 11 o'clock? So we can't actually use this technique to find the instantaneous velocity because we can't divide by 0. So the average velocity uses how many times? 2, because we had to find the change in the distance over the change in the time. So instantaneous velocity uses how many times? 1. So as the time duration after 11 o'clock becomes small, the instantaneous velocity at 11 o'clock is much more likely to be very close to which of these values. So if you had to pick something off the chart, and notice there's fluctuation, it's up and down and up and down. You've driven in a car before. Something happens, you have to put on the brake to slow yourself down, you speed back up. So the best answer would be the one that was closest to 11 o'clock. So 54.5 miles per hour would be my best guess for the instantaneous velocity at 11 o'clock because that's the closest time to 11 a.m. So you might want to kind of look through this, but this is really what I talked about with that little demonstration at the beginning. So you can look through that, and you might notice down here, we've seen this before, right? Because we've been talking about, you've had to do some things like that. As a matter of fact, I had already kind of given you a clue that this is related to the definition of a derivative and looking at the limit on this as h approaches 0. So we're going to 3 formulas that you will need to know. One is for the secant and the slope of the secant line, and then we have the slope of the tangent line. So when you think about the slope of the secant line, they put this, they've written out in this format, which is fine. But you can also just think of it as the change in y. So the regular old slope formula that you are familiar with from algebra, and change in y over change in x. So if you want, you can just kind of think of it that way. And for our slope of our tangent line, because we already know the idea of limits, I'm going to use that notation. So I'm going to call this still the slope of the tangent line is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So I'm going to use this. They're using as your point x naught in a UGHT. I'm just going to use it with this. This is the formula you're going to get very familiar with as we move along. So we have an example we're going to kind of work through. And by the way, you're also going to be using the point slope equation of a line. You know, y minus y1 equals m times x minus x1. We'll use that a lot. So let's work through some examples. For the function f of x equals x squared plus 1, find the following, confirm part C on your calculator. So the average rate of change between x equals 1 and x equals 3. So I'm going to take f of 3 minus f of 1 over 3 minus 1. That's my slope of my secant line. So when I do that, if you plug a 3 in, you're going to get 10. Plug a 1 in, you're going to get 2. So I end up with 8 halves or 4. So that's my average rate of change. To get the instantaneous rate of change when x equals 2, I'm going to be using this formula up here, and I'm going to be plugging in a 2 for the x value because they're telling me what that is. So I'm going to say the limit as h approaches 0 of f, and instead of an x plus 2 or an x plus h on the formula, I'm going to put 2 plus h minus, instead of an f of x, I'm going to put f of 2 all over h. Okay, so again, I'm using this formula in place of the x. They tell me x is 2, so I'm plugging in a 2. But I'm still going to have some work to do here because I have to evaluate what is x plus, or what is f of 2 plus h equal to. I'm also going to need to know f of 2, so I'm going to just figure that out. If I plug a 2 in, I'm going to get 4 plus 1 is 5. So now I'm going to have the limit as h approaches 0. Remember what we do? We put a 2 plus h where the x is. So I'm going to have a 2 plus h, quantity squared, plus 1, minus f of 2, which we already determined was 5, all over h. So I'm going to have to expand this, use the formula, hopefully you know it, or a box, or FOIL. So I'm going to have 2 squared is 4, plus, multiply and double, I get 4h, plus h squared. Then I have a plus 1 and then a minus 5, so I'm going to combine those and get minus 4 all over h. So notice what happens. The 4 and the minus 4 cancel. And then also notice that I can factor out an h. So I get 4 plus h over h. The h's cancel. Now I can plug in a 0, and I get 4. Now, in this example, the average rate of change matches the instantaneous rate of change. That's not always the case. It won't always happen that way. But this time it did. So the equation of the tangent line when x equals 2. So how do you find the equation of the tangent line? The formula is right here. So we're going to have, remember, were you going to use the point f of 2 equals 5? So when I need my x1 and my y1, they're right here, f of 2 and 5. So x is 2, y is 5, and the slope is 4. So I'm going to have y minus 5 equals, my slope I found was 4, and then x minus 2. And I could leave it like that, or I can simplify this to slope-intercept form. And if I add 5, I get negative 3. But you don't necessarily have to unless you are told to. And then it says confirm on your calculator. So let me show you that. So on my calculator, I graphed y equals x squared plus 1. So that was f of x. And then in y2, I graphed my equation of the tangent line, 4x minus y equals 4x minus 3. When I look at that graph, I can see that it does indeed look like a tangent line, but does it actually hit at the point 2,5? So let's find out. If I if I check the value when x equals 2, and it should take me to that point. So I can see that it does look like that point of tangency is happening at the 0.25. So it kind of, that's how you can confirm on your calculator. Okay, for the next example, our function this time is 5x plus 2, which is a linear function. So we're going to calculate the average rate of change. So remember, that's the slope of the secant line. So I'm going to take f of 4 minus f of negative 1 and divide that by, 4 minus negative 1. So if you plug in a 4, you get 22. If you plug in a negative 1, you get negative 3. Here in the denominator, we're going to have 5. So we get 25 over 5, which is 5. That's the slope of my secant line. Now we're going to do the instantaneous rate of change. But first, since we know we're talking about what happens when x equals 2, I know I'm going to need to know f of 2. So I'm just going to find that out right now. And I get 12. So my slope of my tangent line, I'm looking at the limit as h approaches 0. We're plugging in a 2. It's not all, doesn't always have to be a 2. Of f of 2 plus h instead of x plus h minus f of 2 all over h. So then we have to put a 2 plus h where the x is. So I get the limit as h approaches 0 of 5 times 2 plus h plus 2. And then we have minus f of 2, which we've already found was 12, all over h. Next, we would have our limit as h approaches 0. I'm going to distribute. I get 10 plus 5h and plus 2 minus 12 all over h. So 10 plus 2 is 12, minus 12 is 0, so those are gone. And then notice I can cancel out my h's, so I end up with a limit as h approaches 0 of just 5, which is just 5. The limit of a constant is the constant. And once again, our average rate of change equals our instantaneous rate of change. That is not always the case, although in this case, you'll see would be. The equation of the tangent line, y minus 12 equals, my slope is 5, x minus 2. So remember, that's just our point slope form of the line. So if I change this to slope intercept form, and I'm going to get 5x, adding 12, I get plus 2. Now, this is the equation of my tangent line. But look at what f of x was. So that's because this is a line. So if you think about where would it be tangent, it's just on the line. So that's the reason why our instantaneous rate of change equaled our, well, this was that, equaled our average rate of change. And if you have a linear function, that's going to be true for every point on the line. It would be true no matter what the value of x was. So that one was a little different. Okay, next we're going to look and see what happens on this. Now we have a parabola again, but a little bit more complicated than the first one we did. So the first thing we're going to look at is our slope of our secant line. So we're going to take f of negative 1 minus f of negative 3 and divide by negative 1 minus negative 3. So when you do that, if you plug a negative 1 into this function, you're going to get negative 4. If you plug a negative 3 in, so let's see, plugging in a negative 3 gives you a 9 minus 12, negative 3 minus 1, also negative 4. And in the denominator, we're going to change this to negative 1 plus 3, so we get a 2. But notice we have a 0 here. So we get 0 over 2, which is 0. So the slope of my secant line is 0 between those 2 points. So the instantaneous rate of change, we're going to look at the limit as h approaches 0. Oh, let me do this. I'm going to need to know f of negative 2. So that's going to be 4 minus 8 is negative 4 minus 1 is negative 5. So I'll be using this. So I'm going to just write that down. So we're going to have f of negative 2 plus h minus f of negative 2, just using that formula, over h. So now I'm going to have to plug this in. So if I put in a negative 2 plus h, I'm going to have negative 2 plus h quantity squared plus 4 times negative 2 plus h minus f of negative 2, which we already determined was a negative 5, all over h. You're probably wishing you could just extend the page, make it longer, but sorry, write small. So here we're going to square the negative 2, and we get, when we do that, we get a positive 4. Multiply, you get negative 2h. Double it, you get negative 4h. Square the h. And then distribute that 4. We're going to get a minus 8 plus 4h. That's going to become a plus 5. All over, I forgot something here. Oh, I had that plus. Let me go back. Right here. Sorry. And I noted, I'll tell you in a minute how I noticed I forgot something. I forgot this minus 1. I did that part and forgot the minus 1. And then we had minus f of negative 2, which was the negative 5. So I'm going to have a minus 1 and a plus 5. And we have over h. And here's how I knew that. Because if you do this right, then your constant's going to cancel out. So 4 minus 8 is negative 4, minus 1 is negative 5, plus 5 is 0. So my constants cancel out. So I knew that I did something wrong because I saw that, oh, my numbers aren't going to cancel out. So that always would work when you're doing a problem like this. So it kind of catches your mistakes. So then going on the limit as h approaches 0, I'm going to, I could also cancel these out. And we end up with just h squared over h. I can cancel an h, so that's going to be gone. It's just going to be the limit as h approaches 0 of h, which is 0. And I know I keep telling you, they don't have to match, and then all these examples do. So that's the slope of my tangent line at that point. So my equation of my tangent line, y minus a negative 5 is going to be plus 5, equals the slope is 0, x minus a negative 2 is a plus 2. So we get y plus 5. This is just going to be 0. So y equals negative 5. So that's my slope of my tangent line. So let's think about that. If I get a horizontal line, and that's my tangent line to this parabola that, notice, you know what the shape of a parabola is, and it's opening up. So think about where this is, because that's going to be an important thing in calculus we're going to use. When you have a horizontal tangent, that tells you, first of all, that that's going to happen at the vertex of this. So if you imagine a parabola opening up, then that horizontal tangent means that that point, where the point of tangency, is going to occur at the vertex. I'm going to stop here and call this the end of part 1. And and then I'll go on in another video.